Now, next is an example. Every neighborhood is an open set. Every neighborhood means a set of the form NRP is equal to set of x belong to RK with DXP less than R. So, every neighborhood in a metric space is an open set. Let Q belong to E. Let E equal to NRP, which is equal to set of x, not x belong to RK. It is metric space, so x belong to x with DXP less than R. So, correct. This is not RK, X be metric space. Let Q belong to E. We prove that Q is an interior point of E. That is, there exists an H greater than 0 such that the neighborhood NHQ of Q is contained in E. Since Q belong to E, we have DQR, DPQ is less than R. So, put H equal to R minus DPQ. So, R is strictly greater than DPQ. So, R minus DPQ is strictly greater than 0. It is a positive number. Now, consider the neighborhood NHQ, neighborhood of Q of radius H, and let X belong to this. Then definitely DQX is less than H, because this is a neighborhood of radius H, DQX less than H. Then dpx is, by triangle inequality, dpx is less than or equal to dpq plus dqx. dqx is less than h. So, this is less than dpq plus h. But we have h equal to r minus dpq. So, dpq plus h equal to r. So, this is less than r. dpx less than r means what is our E? E equal to NRP, set of x belong to x with DXP less than R. So, we have this x belong to P, that is NHQ contained in E. So, Q is an interior. So, we have any, for any x belong to any Q belong to E, we have any Q belong to E, we have neighborhood NHQ contained in E. So, we have Q is an interior point of E. This is true for all Q belong to E. Hence, E is an open set. So, actually we can see like this. Suppose this is X, this is an equal to R. Let this be an open ball of centered at X, radius R. Take any Q here. Any Q here, then this is dpq, you choose this to be H, then this ball will be contained in this, so that it is a it's an open set. So, every neighborhood is an example for an open set. Now, this is regarding limit point. If P is a limit point of a set, so what is limit point? A point, let E contained in X, P belong to X. P is a limit point of E means every neighborhood of P contains a point of E other than P. This P may be in E or need not be in E. So, every neighborhood intersect E in some point other than P. So, if P is a limit point of a set E, then every neighborhood of P contains infinitely many points of E. That is, if a set has a limit point, that set should be infinite. Suppose to the contrary, that there is a neighborhood N of P which contains only finite number of points of E, and let that be Q1, Q2, etc. Qn, which is equal to N intersection E. N contains only finite number of points of E, with the P not equal to Qi for I equal to 1 to etc. N. Then, since P not equal to Qi for each I, we have dpq1, dpq2, etc. dpqn are all positive numbers, and a minimum of a finite number of positive numbers is positive. So, if we take R to be equal to minimum of dpq1, etc. dpqn, then this R is greater than 0. So, we have R as a positive number. Now, consider the neighborhood. And so, we have P is a point, and we take a neighborhood N which contains finite number of points, and choose R to be the minimum distance from among dpq1, dpq2, etc. and find this neighborhood. So, this is a neighborhood again this is neighborhood of P. Since P is a limit point, this will intersect with E. This neighborhood will intersect with E in some point other than E, so it contains a Q. And definitely this neighborhood is contained in what? Contained in N. R equal to minimum of dpq1 etc. So this neighborhood will be contained in N. Therefore this Q will be contained in N, but Q not equal to Q1, Q2 etc. because distance between P to Q is less than R, which is equal to minimum of dpq1, dpq2 etc. dpqn. Therefore Q not equal to Q1, Q2 etc. But we have taken that N intersection E equal to finite number of points Q1, Q2 etc. Qn. That's a contradiction. Therefore we have that's a contradiction, because if we take this to be finite, we get some point different from this Q1, Q2 etc. Qn, which again belong to N intersection E. Therefore it cannot be finite. Therefore N intersection E is finite. So a finite set cannot have a limit point. Now next question, if E is a subset of R2 which is open, is it true that every point of E is a limit point? So let E subset of R2 which is open and P belong to E. Since E is open, there exists an R greater than 0 such that NRP contained in E, because since E is open, P belong to E, we have P is an interior point of E. Therefore, there exists an R greater than 0 such that NRP contained in E. Now choose N to be any neighborhood of P. We prove that N intersect with E in some point other than P. Then N is open. We have proved that every neighborhood is open. Each N and NRP contains what? Contains P. So N intersection NRP is a non-empty open set. Since finite intersection of open sets is open, this is open. Since P belong to N, P belong to NRP, so this contains P, so this is non-empty also. And since NRP contained in E, we have this contained in E. Now since this is an open set, each point of this is an interior point of this set. So there exists some epsilon greater than 0 such that N epsilon P contained in N intersection NRP which is contained in E. So N epsilon P, a point here, a ball around this of P is contained in E. So this will definitely contain a point other than P, which is contained in E. So we have E. N contains this N contains point of E other than P. Therefore P is a limit point. Now and note that this need not be true when E is any open subset of a metric space. So for that, if X is a metric space, is the same thing true? Need not be, because for example we can take the discrete metric defined by, so you take any X with at least 2 elements, dxy equal to 0 if X equal to Y and equal to 1 if X not equal to Y. So note that the metric D from X cross X to R can take only 2 values, 0 or 1. Now you consider the R equal to 1. So what is NRP? For any P, what is NRP? NRP is equal to set of Q belong to X such that dpq less than 1 by 2. So dpq less than 1 by 2. dpq can take value 1 or 0. It is less than 1 by 2 means it is definitely equal to 0, such that dpq equal to 0, and dpq equal to 0 is possible only if P equal to Q. So it is nothing but singleton P. So since NRP is open, we have singleton P is open with respect to this metric. The singleton is open with respect to this metric. Therefore, but this is a finite set. A finite set cannot have a limit point. So no point of the singleton is a limit point. So singleton P is an open set. P belong to the singleton P which is not a limit point. So, that the same result is not true in the case of metric spaces.